Thank you very much for the introduction. And I first thank Ahmed Abes to invite me to give one talk here. So, okay, so in these talks, I first give a description of a prismatic crystal. I should put local. And it's homology. Oh, okay. So, in terms of q-Higgs modules, and it's q-Dolbeault form. Thank you. But not for a general prismatic site, but when a base is defined over q-crystalline prism. Base is defined over crystalline prism. So this is the first topic, and then I try to apply this to a comparison between prismatic homology and A inf homology with coefficients. And for inf-cohomology is introduced by Butt, Morrow, and Schultz for constant coefficients, and its coefficients. So for coefficients, I studied with Matthew Morrow and wrote one paper, and also show that coefficients which we call relative PKF modules, and actually the categories is related to these prismatic crystals, and so but we didn't compare that cohomology of the two coefficients. So today I'd like to compare it. Okay, so first I start with first topic, and for this topic we already have some work on this topic. So first I discuss, so in the joint work with Morrow, we discuss about the description of prismatic crystal when the base is A inf. That's a quite special case. And also, Ian studies the case of hot state crystal. And also, he studied also the cohomology, and also August studies the case p-crystalline prism, and recently Groh, Lustum, and Hiros released new preprints on the same topics actually, and they say that they assume the variety is one-dimensional for simplicity, and but so I think they have the same results on this. So, but in this talk they really study the stratification correspond to the crystals explicitly, and then showed this and gave a description, at least in the one-dimensional case. But here I tried to follow the approach with my joint work with Morrow. And so our approach relies on the gamma action. And then we construct Q derivations using that gamma action, and I tried to generalize it to to this kind of base. Okay. So in these settings, so in this joint work, so we start with perfectoid field. And O is the ring of integers of this one, and we consider the A inf of O, so which I simply write A inf in this lecture. And then so for simplicity, we try to explain in this simplest case. I mean the periodic completion of this polynomial ring. So this is a power series ring, and then we consider the endomorphism of A, the automorphism of A, defined by just Tj goes to Tj as to I and Tj to if I J is equal to I and J is not equal to I. And Q is just something like this. I don't explain precisely, but maybe you can guess. If you know A inf, then you can easily guess, I think. Q to P. Okay? And then we consider the derivation like this. Q minus 1 and minus 1. And consider the Q connection with respect to this derivation. Sorry. Q. Just we want to consider Q deformation or something, q-Higgs module. Okay, so then, okay. So, yes, if you work with Q, so then you just usual Q derivation, but so, yeah. Okay, so, yeah, so if you use this derivation, you get you get this. And so this is a Q analog of integers, so maybe. So this is, so in some sense, yeah, so q-Higgs module is actually Q deformation of P connections. And so here multiplication by P appears. And then, so the advantage of starting with gamma I is that gamma I extends to étale covering, étale scheme. I don't know, étale algebra, yeah. Or prismatic envelope. Yeah. Yeah, so this is, it's better to say. I'm sorry. Yeah. And then, so I tried to generalize this construction to a general, not only a inf, but for a general prism over this q-crystalline prism. But then, in general, we cannot divide by q minus 1, and this causes a trouble. The typical case is q equal to 1, and then that case is the gamma action is trivial, so you can't apply this construction. But I'd like to construct a uniform way to deal with the case q minus 1 is a non-zero divisor, and also the case q is equal to 1. Okay. And so this derivation satisfies this following equality. For any x, y in A. So this is easy to see. Yeah, this equality holds for gamma I minus 1, and this also holds after dividing by q minus 1. And if you put, by definition, gamma I is described in terms of this derivation. So then you get, I'm sorry, I is here. Yes. Which one? No, so this is in some sense a logarithmic derivative. So no, so yeah, so for example, yeah, so this is, if you apply this, you get this goes to this one. So this is in some sense a pure deformation of so it's in some sense logarithmic derivative. So if you want to have n minus 1, I have to divide by ti further, but I don't do that here. Is it okay? So maybe so. Yeah, this term is this term is something like the sum of this one and this one. Okay. Which one? You mean what's this one? Is there any problem? Okay. Okay, so so then I will try to so maybe so just okay, so maybe I think it's better to divide into, so okay, so and I just study this kind of endomorphism in a general setting, so but not so very general, but R is a ring and A in R algebra, and Q is an element of A. And I define the set of map from A to A, which is R linear, and satisfying this property, dxy is equal to x dy plus so this becomes opposite. Sorry. Yes. And then so this so if you consider this twisted derivation, so in the case of usual derivation on A modules linear over I, so in that case, such derivation is interpreted in terms of sections of extensions of A by A modules. And such we also have such description for this twisted derivation. So I first explain it. It's quite simple. So I just define E sub q of A to be the quotient of a polynomial ring divided by t times t minus q minus 1. And then it is quite easy to prove that this derivation is just corresponds to the section of this A algebra. So this is the A algebra, and this has an augmentation I wrote by pi 0, which t goes to 0, and the condition is just pi 0 s is equal to identity. And the correspondence is just given by, it's quite simple. SE, so x goes to x plus q minus 1 dx. Yes. Okay. So then, so for example, so this in this description, if we are given an ideal I of R, and if which contains q minus 1, and then the T of EQA, so which is the kernel of pi 0, is iadically nilpotent. So this is easy to see because n plus 1th power of t is just q minus 1 times nth power of q minus 1 times t. And if q minus 1 is contained in this ideal, so this allows us the unique extension of D under iadically et al. Form. So this definition is complicated, but if you use this description, you can easily show that this is a twisted endomorphism uniquely extends to et al. homomorphism. Yeah, so this is quite easy to show. So then, so I'd like to explain. One can also prove the extension, unique extension under prismatic envelope. And so to do that, I have to explain compatibility of D with delta structure. And what is delta structure on a ring? So delta structure on a ring, I quite briefly recall. So this is a map from R to R, such that the map from W to the ring of bit vectors with of length 2, defined by x to the x delta x, is a ring homomorphism. Yeah. And so this condition implies that R to I, which tends to x, is p square of x plus p times delta x is a homomorphism. And if p is a non-zero divisor, and this condition is equivalent. So this is also easy to check by using the explicit formula defining the multiplication and addition of these bit vectors. Okay, so then what the compatibility of D with delta structure should be. And so I will try to explain it. So before that, so the most important example in this talk of delta ring is this one with delta q is 0. So if you explain this, if you consider the corresponding endomorphism R, phi, so I denote it by phi, this means that phi q is phi q goes to q to p power of q by phi. Yeah. And I consider and in this definition, I take R to be a delta algebra over ZQ. So R also has a delta structure compatible with this delta structure, and A is also delta algebra over A. So A has a delta structure compatible with that of R. Okay. And we consider this derivation, and the compatibility is related to this question. So if we consider the sum of identity map plus q minus 1 times d, so this is an endomorphism of A. So this is easy to see. This is easy to see just by this formula. But the point is that in our setting, D is not defined by gamma D in general because Q minus 1 may not be a non-zero divisor. But we want to consider the following question when gamma D is a gamma homomorphism, delta homomorphism. Delta endomorphism of A. And so if you write down this compatibility explicitly, it's very complicated. So I just explained the interpretation of this condition in terms of the ring EQ of A. So this is actually quite easy. So this is lemma 2. Okay. Yeah. So I put C to be this one. So this is actually divisible. You can compute. Actually, so this is p torsion free, so it's better to compute it in terms of phi. So then you can easily compute, and this becomes and then exists a unique delta algebra. Delta A algebra structure on E delta A such that I don't know, the value of delta T is just Ct. Yes. So E delta, I'm sorry, thank you, EQA. Yeah. Okay. So the proof is actually not very difficult, but so maybe using interpretation of the map from R to W2 of R. So maybe the proof is that we have a map defined by the given delta structure on A, which sends x to x delta x. And we want to extend this to this EQ. But I first do this to the polynomial ring. So this is, of course, possible. So just T goes to Ct. And so one can show that the image of T square goes to the image of T square is the same as image of Ct. So this can so we can show this one. So this is just a computation. So actually, this is quite easy to check. And then remark is that if you so from EQ of T, we have another map. I write it by pi sub q, so which sends T to T, which maps T to the q minus 1. So this is and so then this is a delta homomorphism. So this is easy to see because by definition, delta t is equal to ct. But if you put q minus 1 instead of t, then this equality holds because c is the quotient of delta q minus 1 by q minus 1. So yeah, but this property is quite important. And so then I define derivation, q derivation compatible with delta structure to be just q derivation such that the corresponding section of EQ of A is a delta homomorphism. Okay. Let me see. Yes. So then by this remark, if you take an derivation, Q derivation, I don't know how to say. So this the element of set, element D of this set. So then actually, so gamma D is a composition of pi Q and SD. SD is just a map corresponding to D. So this is X goes to X plus Q minus 1. Oh, I'm not sure whether. I'm sorry. So I should write T-dx. I forgot whether I may have made a mistake, but it disappeared. But so this should be T. If I wrote Q minus 1 here, please correct. I'm sorry. So this should be T. And so then if you compose the two, so then so X goes to X plus Q minus 1 dx. So this is and we know that pi Q is a delta homomorphism, and by condition, this is a delta homomorphism. So the condition is, yeah. So this is a delta hom. Okay. And this description allows us to show that under certain condition, so the unique extension of D under D above under prismatic envelope. But actually, I need some condition. So maybe I explain a little bit more. So if you are given a prism and A is a delta algebra over A, and J is an ideal of A containing IA, then I need to assume that R. I'm sorry, I made many mistakes. I'm sorry. Yeah, over R. Any other mistake? Sorry. So, yeah. So So if the image of D of JA is contained in IA, then D extends to the prismatic envelope of AJ over RI. Okay. So now I can state my theorem for the first topic. And so, I don't have time, so I'm sorry, so I didn't explain the definition of prism. So I consider the bounded prism over R, of prism R over this Q crystalline prism, and R bar is, as usual, the quotient of R by this Q analog of P, and X is a p-adic formal scheme. And then the prismatic site is looks like this. The object is a map like, so just quite a rough review, but so I'm sorry. So this strange notation was P is a prism. Yeah. Over R. And also we have a map. So we are given a prism over R, and we have a map from X to P, from a formal scheme of P bar to X, and P bar is the same, is defined similarly to R bar. So this is and the prismatic site, and the topology is a flat topology. Yes. Okay. And since we are interested in a local description, so I assume that X is affine, and we are given an embedding into a formal smooth scheme, a formal scheme smooth over a formal scheme of R. And here we have a map. So we are given, so this is given. And also the coordinates is given. That assumes that this is invertible. Actually, we, if you work with I will work with a logarithmic derivative, but actually we can also work with the usual derivative. So So nth power goes to n minus 1, then you can remove the assumption that this is a unique. So you mean this one? Right, but I have to assume that some assumptions assume that bounded envelope, bounded prismatic envelope exists for this embedding. But so basically, I'm interested in the case x is smooth over R bar. But I think so this also the existence. Yeah, you can also prove this existence by when x is locally complete intersection and flat over R bar. Okay, so then using the above general definition of this Q derivation, one can construct theta I, so Q analog, Q analog of how to say P derivation, yes. That's that. So having the same property I explained before. So if J is equal to I, so I just write it down for, I forgot to write the very important condition. So this is, so given exists one delta structure, there is a unique delta structure such that delta Ti is equal to 0. So use this delta structure. So if you consider the lifting of Frobenius corresponding to delta structure, so then Ti goes to the piece power of T. And so this is the delta structure we consider. And then we take the, with respect to this delta structure, we take the prismatic envelope. But if you take the prismatic envelope should be bounded. So because otherwise, so I'm sorry. So I forgot to write I'm sorry. I made many mistakes. So this should be bounded. Yeah. Yeah, because without this, so, but I didn't define bounded, so maybe you don't care much about this. So maybe, so then you can construct this endomorphism, yeah, first on B by using the by using the description of Q derivation in terms of section. To construct a section is quite easy. And so if you're given the coordinates, you can take a section, and also you can extend it to étale cover. So maybe you can define theta I on B, and then you take the extend it by this description. No. So by this claim, so this extension property, and by condition is satisfied because we send Tj to this element, and this is divisible by Q analog of T. Okay. So then we define the map theta by sending P log Ti. And omega c is a by c by module. Yeah, is a c by module. And let me see. Omega c is a c by module, and left action is the usual action, and the right action is just given by multiplication by x is given by left multiplication of gamma ix. And gamma I is identity plus q minus 1 times theta I. And then I can state the theorem, first theorem, and I state the theorem in the discrete case because I mean the topology is discrete, so to avoid some difficulty in working with completion. So we take an ideal which is open with respect to the p-adic topology on R, and then you can describe crystals killed by J in terms of q-Higgs module killed by J. So we modulogy. So this is equivalent to I can't explain what is module-based integral connection for this setting. But actually, so the general theory is developed by Yves Andreev, and I can apply it to this twisted setting. And you can define module-based connection over this C mod J and theta mod J. And so then we have this equivalence, but we need some, so I don't know how to say. So Q convergent? No, convergent. Quasi-nilpotent. Yeah. And secondly, if you are given an element in here and a corresponding element in here, and then you also have an isomorphism. That is prismatic cohomology in this local setting is simply described in terms of complex, so Dolbeault complex, q-Dolbeault complex associated to this module with integrable connections. And the proof, I'm sorry, so I don't have time, but for the first one, over A inf in the joint work with Morrow, so we proved this kind of equivalence by using the derivation coming from gamma I. And so by some modifications, you can apply it to this general setting. So this is basically the same as going to work with Morrow. So I didn't analyze the precise description, description of the, how to say, a stratification. So I just construct a stratification using this this q-Higgs field, and then finally we reduced everything to the case modulo q minus 1. And for 2, so the key fact is the Poincare lemma, and I proved the Poincare lemma as follows. So just take an object of this prismatic site, and then we consider the bounded prismatic envelope. Envelope of the base change of the smooth formal scheme B to the P, and then we have a map from P to the P because P bar, P bar because so let me see. We have a map from no, B to the P bar because B maps to A and A maps and A. We have a map from A to P bar, so we have this map, and then we have a following resolution. So for any CP mod J module, let me see. No, so P mod J module, we have a following map. So this is theta is a resolution. So so I also think we should write here some theta here. No, this is not a usual drum complex. So so this is a resolution. Yes, but actually in the work of Groh and Lustum and Kiros, so they work with stratification, and actually you can prove also a Poincare lemma using such. So they work with that. So maybe it might be better, but actually anyway, so we can define theta on any this kind of prismatic envelope. So you can prove this kind of Poincare lemma for any bounded prism over R. Okay, so now I only have 5 minutes. So but maybe that's because I made many mistakes. So I'm sorry. It's my I'm sorry. But I give a few words on the second topic. So second. So comparison with A inf-cohomology. So in this case, we take the R to be A inf of O. O is the ring we take in the beginning. Yeah, and Q is theta, and R bar is then just the ring O. And so we consider p-adic formal scheme over O, but we p-adic formal scheme. But we assume that this is smooth. And then we have a relative BKF module, which lies in the category of A inf. So actually, locally free, finite locally free A inf module on X, and X is the generic fiber of this formal scheme, and we know that we have a fully faithful functor from finite locally free prismatic crystals of all modules not divided by J. So this is topological one. And so we have this functor. And so if you are given crystals, and you get this A inf sheaf of modules on this. I'm sorry. So this is the pro-étale site. Yeah. And actually, so this is not essentially surjective, but if you are, so slightly, the category is slightly, I don't have a counterexample, but here we need some convergence of some action of the endomorphic theta I, but here we don't have it, so it's something like that. So if you are given a Frobenius structure, so then this becomes equivalence of categories. So yeah. So this is shown. This is shown in the joint work with Morrow, and so what one can prove is the following. Let me write the second theorem. And A omega of this BKF modules is canonically isomorphic to this as projection of this crystal to the étale side of this formal scheme. So I should write it to x8. And the left-hand side is defined by the usual way. So this is some collage of this projection of M to the pro-étale side. So nu is x eta pro-et to x8. So then how of course, this is known for the constant coefficient. So this is proven by Barton Schultz in their paper on prismatic homology, the first paper. But so here so this is analog. It's analog for coefficient with coefficients. And so how to prove this? So the point is that so for the left hand side, so we already know that locally this is described in terms of the q-Higgs modules. So locally we know that this is isomorphic to the q-Dolbeault complex, and also we already know that this is also described in terms of q-drum complex. So to globalize, I just use classical techniques. That is, we take just a fine covering how do I write it? Just so x is maybe say a proper over this one, and so in general this is not affine. But if you take some eta covering, and then you can, or the risky covering may be enough, but then you can take, for example, a lifting to this formal scheme R. So I mean, this is a inf. For example, yeah, so it's not necessary, but for example, you can make this Cartesian. But anyway, you can take this one. And if you take the iterated product of this one, then you can embed it into the product of this one over R. So then you can take the just a prismatic envelope. You get a description of this one in terms of simplicial complex consisting of Dolbeault complex on each on each prismatic envelope. And also we can construct a map from such semi-simplicial complex to this one, by giving some corresponding description of this in terms of perfectoids given by taking some p-truth of coordinates of P, or some product of P. I'm sorry, I can't explain well, but I will stop here. Thank you.
Question or comments?
So you were working over this q-drum prism, but there is even a smaller prism, which is like FP cross invariance inside that. Like there is a sub-prism inside this q-drum prism.
You mean a q-crystalline prism? Also?
Yeah, like the one you started with, like the ZP, where ZP double brackets q minus 1.
Yes.
So there is a sub-prism inside that. So this prism has an action of ZP cross.
So what kind of prism you consider? So you mean a sub-prism is a sub-ring, you mean?
Yeah, so here usually you take this element PQ. Yeah, you take the invariance and the FP star.
FP? You mean,
Is everything working under this prism as well?
I didn't think about it, so I can't answer. So
no problem.
Thank you for your question.
Aqui you can activate your
Akil, can you activate your microphone? Yes.
Oh, it's on.
On.
Hello?
Hello.
Hello.
You can ask your question.
I have a naive question.
Yes.
about you in your local description, you had x embedded in, I think, a y, where y had coordinates.
Coordinates. Yes.
Yeah, you took the prismatic envelope of x and y, where y had these coordinates, t1 to tn, with p of ti equal to ti to the p. And I'm wondering if it's a naive question, can you make it more global by having y be projective space? Coordinates like this?
Yeah, it's an interesting question, but projective. Yeah, but yeah, that's a good question, but I don't have an answer yet. Yeah, actually, I did think about it, but yeah, so because you have projective space, if you work with that, yeah, you have a global description in some sense. Yeah. Yeah. So yeah, that's a good question. But yeah, but in that case, I think yeah, I'm not. I forgot. I had some difficulty, but I couldn't remember. I can't remember. I'm sorry. So yeah.
It's not obvious to me at all, but because you have these extra operators, which I don't understand so well. But what I didn't understand in the last part, in comparison theory, you use a simplistical technique.
Yes.
To do the global local calculation, but if you have coordinates, I don't see how the simplistical techniques work out so well. Because you actually use the coordinates, so you have to show that these operators are compatible with the coordinates somehow.
Yeah, but so if you take the products, you can take the coordinates of each component. We have you obtain coordinates of the on the product, and also it's compatible with simple shell structure. Yeah. So is it okay? Or is there? I hope I hope that I didn't make a mistake. Yeah, but is it okay?
Let's thank Takeshi-san again.